October 23rd, 2025. An ordinary Thursday when most people were heading home from work, planning their evening, scrolling through news on their phones. And then, a headline that makes your breath catch. NASA has activated its planetary defense system for the first time in history for an interstellar object. Not for an asteroid from our solar system. Not for a comet born somewhere in the Kuiper Belt. For a visitor from beyond. For an object designated 3I Atlas that came from interstellar space, from that abyss between the stars where our sun's laws don't apply. International Business Times broke the story first. The International Asteroid Warning Network, known as IAWN, approved by the United Nations, officially designated 3I Atlas as the target of a coordinated observation campaign under planetary defense protocols. This was the first time in history such measures were applied to an interstellar object. The words planetary defense instantly spread across social media, sparking a wave of questions, theories, and debates. Drop in the comments where you're watching from and how much time you've got, because this story requires calm and attention to details that often get lost in the noise of information overload. To understand the scale of what's happening, we need to go back a few months. July 1st, 2025, a nighttime observatory in Chile, where an automated telescope from the Atlas system operates, the Asteroid Terrestrial Impact Last Alert System, a system designed to detect potentially hazardous objects, scanning the sky with the indifferent precision of a machine. And there, among thousands of captured frames, the algorithm picks up something unusual. The object is moving too fast. Its trajectory doesn't match any known orbit. This isn't equipment error. Repeated images confirm it. We're looking at something that shouldn't be here. Astronomers dive into calculations. The object's velocity exceeds any reasonable values for bodies bound by the sun's gravity. The orbital eccentricity, a measure of how much the trajectory differs from circular, is off the charts. This is a hyperbolic trajectory. The object isn't orbiting our star. It's passing through the solar system, like a traveler crossing foreign land on a straight road, the third interstellar object in the history of human observation, after Oumuamua in 2017 and Comet Borisov in 2019, hence the designation 3I, third interstellar. But 3I Atlas is different from its predecessors. Oumuamua was a mystery of shape, elongated, dark, silent. Comet Borisov behaved predictably, showing activity typical of comets in our system. But this new visitor had a surprise. A coma is forming around the nucleus, a cloud of gas and dust, but not the usual color. Green. A rich, almost emerald shade that indicates the presence of diatomic carbon in the gas envelope. This color appears when sunlight breaks down organic molecules in cometary material. A green comet from interstellar space, an image that instantly captures the imagination. The nucleus shape, as far as early observations could determine, is elongated, not as extreme as Oumuamua, but definitely stretched out, like a fragment of something larger, torn off by unknown forces and sent on an infinite journey between the stars. The size is estimated at several kilometers in length. Exact figures are still being refined because the object is moving fast and every observation is precious. Astronomers around the world are pointing their telescopes at this point in the sky, trying to collect maximum data before the visitor returns to interstellar darkness. And now, almost 4 months after discovery, October 23rd brings an unexpected announcement. IAWN. This abbreviation needs explanation. The International Asteroid Warning Network wasn't created out of nowhere. February 15th, 2013. The city of Chelyabinsk in Russia wakes up to an ordinary morning. and suddenly the sky tears open with a fiery trail. A meteorite, about 20 meters in size, enters the atmosphere at 18 kilometers per second. The explosion at an altitude of about 30 kilometers releases energy equivalent to 500 kilotons of TNT. The shockwave shatters windows in thousands of buildings. More than 1,500 people are injured, mostly from glass shards. The Chelyabinsk meteorite became a wake-up call humanity couldn't ignore. Until that moment, the topic of asteroid danger existed mostly in scientific literature and Hollywood movies. But this was reality. An object the size of a small house caused serious damage to a major city. And most alarming, no one saw it coming. All early detection systems missed this rock because it came from the sun's direction, from the blinding light where telescopes are helpless. It was a blow to the overconfidence of those who thought we had control over near-Earth space. The global community responded. In 2014, the United Nations approved the creation of an international coordination system to counter the asteroid threat. IAWN became one of the key elements of this system, a network connecting space agencies and observatories worldwide. NASA, the European Space Agency, Roscosmos, the Japan Aerospace Exploration Agency, Chinese and Indian agencies, all joined this initiative. The mission: detect potentially hazardous objects, track their trajectories, coordinate observations, and in case of real threat, activate defense protocols. The system works on a multi-level verification principle. When an object is discovered that might be of interest from a safety standpoint, the classification process begins. The orbit is calculated. The probability of Earth approach is determined. Size and composition are assessed. Most objects are quickly removed from the threat list. Their trajectories pass far enough away, or their sizes are too small to cause significant damage. But for some objects, heightened attention mode kicks in. A coordinated observation campaign is activated. And here's where the key question arises that concerns everyone who learned about the October 23rd news. Why did IAWN activate planetary defense protocols for 3I Atlas if NASA's official calculations show the object will pass at a distance of 1.8 astronomical units from Earth? An astronomical unit is the average distance from Earth to the Sun, roughly 150 million kilometers. 1.5 times the distance from us to the Sun. That's an enormous distance, safe by any measure. Even if the trajectory changed slightly, the safety margin is colossal. So what's going on? There could be several explanations, and all of them require calm analysis without panic. The first and most likely: this is a routine scientific campaign using IAWN infrastructure to coordinate observations of an extremely rare phenomenon. Interstellar objects visit our system extremely rarely. We only know of 3 in the entire history of astronomy. Each such visit is a unique opportunity to study material from another star system, to understand planet formation processes in other corners of the galaxy. IAWN activation ensures observation consistency. All the world's largest telescopes work according to a unified plan. Data is standardized and accessible to all network participants. The second explanation relates to safety protocols. The system requires activation for any object with anomalous characteristics, even if there's no direct threat. 3I Atlas demonstrates unusual behavior: green coma, elongated shape, trajectory from interstellar space. This automatically makes it an object of increased attention. Protocol dictates collecting maximum data to ensure there are no hidden risks. For example, cometary activity can create reactive forces that slightly alter trajectory. For a regular comet, this isn't critical. But for an interstellar object whose trajectory is being calculated for the first time, every detail matters. The third possible explanation is logistical. In late October and early November 2025, 3I Atlas goes through a period of solar conjunction. This means that from an Earth observer's perspective, the object ends up in line with the Sun, hidden in its blinding light. These are precisely the periods when objects are hardest to track. IAWN activation allows coordination of observatories in different hemispheres, use of space telescopes working in infrared where sunlight is less problematic. This guarantees the object won't be lost from sight during the critical period. It's important to understand, activating the planetary defense system doesn't equal confirmation of threat. This is a tool of science and coordination that works proactively. Better to collect an excess amount of data and confirm safety than to miss an important detail due to lack of observations. The Chelyabinsk meteorite story taught us exactly this. Even small objects require serious attention, and an interstellar visitor with unusual properties, even more so. To understand what exactly happened on October 23rd, we need to break down the architecture of the system that guards our planet from cosmic threats. The International Asteroid Warning Network isn't a single organization with a central office and director. It's a network of voluntary coordination connecting dozens of observatories, space agencies, and research groups worldwide. Each participant has their own instruments, their own areas of responsibility, but they all work according to common protocols, exchange data in real time, and follow a unified decision-making chain. At the center of this network are three main orbit computation centers. The first, NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory in Pasadena, California. This is where the database of all known near-Earth asteroids and comets is maintained. Trajectories are calculated decades ahead. Collision probabilities are determined. The second, the European Space Agency's Near-Earth Object Coordination Center in Frascati, Italy. The third, the Minor Planet Center of the International Astronomical Union in Cambridge, Massachusetts. These three nodes receive observational data from all corners of the planet, verify its reliability, compute orbits, and distribute information back to the network. When a new object is discovered, a standard procedure kicks in. First observations go to the Minor Planet Center. There, data undergoes preliminary processing. The object is assigned a temporary designation, usually a combination of letters and numbers, as was the case with 3I Atlas, initially called A11PL3Z. Then, other observatories receive notification and point their telescopes at the indicated area of sky for confirming observations. The more observation points, the more accurately the orbit can be computed. 3 to 4 observations give a rough estimate. 10 to 15 allow calculation of trajectory with reasonable accuracy. Hundreds of observations over weeks and months create a model you can trust for predictions years ahead. But 3I Atlas turned out to be a special case. Already the first calculations, made in the days after the July 1st discovery, showed the orbital eccentricity is greater than 1. This is a mathematical indicator that separates closed orbits from open ones. Everything that orbits the Sun, planets, asteroids, most comets, has an eccentricity less than 1. Their orbits are elliptical, closed. They return again and again. But when eccentricity exceeds 1, the trajectory becomes hyperbolic, open. The object comes from infinity, swings around the Sun, and heads back to infinity. Forever. Such objects are exceptionally rare. Before 2017, they hadn't been detected even once. Theory predicted their existence. The galaxy has 300 billion stars, and some of them eject material into interstellar space during planetary system formation or gravitational interactions. But detecting such an object is extremely difficult. They move fast, don't emit their own light, are only visible in reflected sunlight. October 19, 2017 became a turning point. The Pan-STARRS telescope in Hawaii detected an object moving too fast and on the wrong trajectory. They named it Oumuamua, in Hawaiian meaning scout or first messenger from afar. Oumuamua raised more questions than answers. The object's shape turned out to be extremely unusual, elongated like a cigar, with a length-to-width ratio of roughly 10:1. Such geometry isn't typical for asteroids or comets in our system. Low reflectivity, reddish color, no signs of cometary activity, no coma, no tail. But the strangest thing emerged in detailed trajectory analysis. Oumuamua experienced weak but measurable acceleration not explained by gravity alone, as if something was pushing it. Comets do this. Gas outgassing creates reactive thrust, but Oumuamua showed no cometary activity. This mystery still isn't definitively solved, spawning numerous hypotheses, from exotic forms of ice to, frankly, quite bold suggestions about artificial origin. August 30th, 2019 brought the second interstellar visitor. Gennady Borisov, an amateur astronomer from Crimea working with his own telescope, discovered an object that quickly confirmed its interstellar nature. They named it 2I Borisov, second interstellar. Unlike the mysterious Oumuamua, Borisov behaved like a classic comet. Bright coma, long tail, ice sublimation under sunlight. This reassured the scientific community, meaning not all visitors from beyond behave anomalously. Borisov's composition turned out similar to solar system comets, but with some differences in chemical element ratios. This allowed conclusions that planetary system formation processes can vary, but basic chemistry is similar. And now, 6 years after Oumuamua, a third appears. 3I Atlas combines traits of both predecessors. Like Borisov, it shows cometary activity. The green coma indicates ejection of organic molecules, but the nucleus shape is elongated, and there are reports of anomalies in brightness distribution, reminiscent of Oumuamua's mysteries. The photometric center, the point of maximum brightness, doesn't coincide with the expected center of mass. This could indicate uneven material distribution, complex surface structure, asymmetric gas outgassing, or something we don't yet understand. These anomalies most likely served as the reason for IAWN activation. The system doesn't wait until a threat becomes obvious. It works proactively. Any object with unusual characteristics goes on the priority observation list. And here, it's important to understand how coordination actually works. When IAWN announces an observation campaign, it means all available resources of the global astronomical network are directed at one object on a coordinated schedule. Telescopes in Chile begin observations at dawn, when the object sets below the horizon. A few hours later, observatories in the Canary Islands pick up the relay. Then Hawaiian and Californian telescopes enter the game. Round-the-clock tracking without breaks. Such campaigns have been conducted before. One of the most famous was connected with asteroid Apophis, official designation 99942 Apophis. This is a near-Earth asteroid about 370 meters in size, discovered in 2004. First orbital calculations caused real alarm. The probability of collision with Earth in 2029 was estimated at 2.7%. This might seem like a small figure, but for an asteroid of this size, even such probability means potential regional-scale catastrophe. Subsequent observations refined the orbit, and the collision threat was ruled out. But Apophis will still pass very close, April 13, 2029, at a distance of only 38,000 kilometers from Earth's surface. That's closer than the orbit of geostationary communication satellites. The asteroid will fly through an area where thousands of artificial spacecraft operate. IAWN decided to use this approach for training. During the period from October 2020 to April 2021, a coordinated observation campaign of Apophis was conducted. It was treated as a new object, as if just discovered, and representing a potential threat. More than 40 observers and modelers from different countries participated in this campaign. Each new observation was entered into the database, the orbit recalculated, collision probability estimates updated. At first, the probability was high, due to lack of data. As information accumulated, the orbit was refined and probability decreased. When it became obvious that the real Apophis wouldn't collide with Earth, a synthetic clone was introduced into the model, a hypothetical object with a slightly altered orbit that would pose a threat. This allowed testing the entire chain, from detection to assessment of possible impact consequences. The key conclusion of the Apophis campaign was understanding the importance of early measurements of object size. To assess collision consequences, it's critically important to know the asteroid's diameter and mass. Ground-based optical telescopes provide brightness information, but brightness depends on size and reflectivity. A dark, large object can be as bright as a light, small one. Infrared observations, especially from spacecraft like NEOWISE, allow measurement of thermal radiation directly related to size. The earlier this data is obtained, the more accurate the consequence models. The same logic applies to 3I Atlas. The comet nucleus size is estimated in the range from 320 meters to 5.6 kilometers, almost a 20-fold difference. Such uncertainty is related to the nucleus being shrouded in a coma, a cloud of gas and dust that scatters light. Separating nucleus light from coma light is extremely difficult. The Hubble Space Telescope and James Webb Space Telescope were directed at the object in attempts to clarify these parameters. Webb, working in the infrared range, was able to conduct detailed analysis of the coma's chemical composition. High concentration of carbon dioxide, traces of carbon monoxide, carbonyl sulfide, water vapor, cyanide, and even atomic nickel. The latter is especially interesting since metal ejection is characteristic of comets when heated. All this data flows into a unified picture. 3I Atlas isn't just another comet. It's a time capsule that flew in from another star system. Some researchers suggest the object's age may exceed 4.5 billion years. It could have formed before our sun was born. Chemical composition, isotope ratios, material structure. All this carries information about processes that occurred in that distant system where this comet was born. Perhaps it was ejected by gravitational interaction with a giant planet similar to our Jupiter, or it was knocked out by a nearby supernova explosion, or it was part of a planetesimal destroyed by collision at the dawn of planetary system formation. IAWN activation for 3I Atlas is recognition of the moment's uniqueness. Such objects don't come often. Statistical models predict that several interstellar objects pass through the inner solar system each year, but most are too small or too dim to be detected by modern telescopes. We only see the brightest, the largest, and each one is a lottery win for science. To understand why 3I Atlas attracts such attention, you need to imagine the scale of its journey. This object didn't just fly in from the distant edges of our system, like ordinary comets from the Oort cloud. It came from beyond, from interstellar space, where distances are measured in light years, where temperature is close to absolute zero, where there are no stars, no planets, no gravitational anchors, only cold darkness and the rarest hydrogen atoms scattered in the void. Imagine an object that drifted in this abyss for millions, possibly billions of years, slowly moving through galactic night until the randomness of trajectory brought it to our sun's neighborhood. Calculations reveal something astonishing. The orbital eccentricity of 3I Atlas is 615, plus or minus 0.17. This is the highest figure among all known interstellar objects. For comparison, Oumuamua's was about 1.2, comet Borisov's about 3. The higher the eccentricity, the more elongated the trajectory, the faster the object moves, the more obvious its alien origin. This isn't a measurement error. It's a fundamental property of the trajectory. The object literally pierces our system like an arrow through a target and will never return. 3I Atlas's velocity exceeds 210,000 kilometers per hour. That's roughly 58 kilometers per second, tens of times faster than planets move in their orbits around the sun. Such speed is only possible for an object not bound by our star's gravity. Earth moves at about 30 kilometers per second, and that's enough to maintain a stable orbit. But 3I Atlas races almost twice as fast, and the sun's gravity only slightly curves its trajectory, turning a straight line into a gentle hyperbola. Entering the system, the object slows under solar attraction, reaches minimum distance from the sun, perihelion, and then accelerates again, heading into interstellar void. October 29th, 2025, perihelion date. On this day, 3I Atlas will be at minimum distance from our star, 1.36 astronomical units, which is approximately 204 million kilometers. This is roughly at Venus's orbital level, a bit farther from the sun than the system's second planet. For a comet, this is a critical moment. Solar radiation heats the surface of ice and frozen gases, triggering intense sublimation, direct transition of matter from solid to gaseous state. It's during these days that 3I Atlas's activity should reach maximum. Gas and dust ejection will intensify, the coma will become brighter, the tail longer. But there's an observational problem. In late October 2025, 3I Atlas passes through solar conjunction. From an Earth observer's perspective, the comet ends up almost in line with the sun, hidden in its blinding light. This is the most inconvenient moment for astronomers. Even the most powerful telescopes can't be pointed too close to the sun. The risk of damaging sensitive optics with solar rays is too great. Regular ground-based telescopes can't observe sky areas closer than 10 to 15 degrees from the solar disk. Space observatories have protective shields, but their capabilities are also limited. This is exactly why coordination of international efforts becomes critically important. While 3I Atlas is hidden behind the sun from Earth's perspective, it can still be observed from other positions. October 3rd, 2025, the comet passed by Mars at a distance of 28 million kilometers. Orbital spacecraft working around the red planet, Mars Reconnaissance Orbiter, rovers with cameras, got a unique opportunity to observe the interstellar visitor from a completely different angle. From Mars's perspective, the object's brightness reached 11th magnitude, at the limit of visibility for orbital cameras, but still accessible for detection. The European Space Agency didn't miss this opportunity. The ExoMars and Mars Express spacecraft in Martian orbit pointed their instruments at the passing comet. Spectrometers analyzed the coma's composition. Cameras recorded tail structure. Particle ejection velocity was measured. These observations from Mars filled gaps in data that inevitably arise with Earth observations due to the planet's daily rotation and weather conditions. When an object sets below the horizon at one observatory, it's visible from another. But Mars provided completely different observation geometry, allowing the comet to be seen at an angle unavailable from Earth. Interestingly, 3I Atlas's orbit lies almost in the ecliptic plane, the imaginary plane in which solar system planets move. The inclination to the ecliptic is only about 5 degrees. This means the comet moves almost in the same plane as Earth, Mars, Jupiter, and the other planets. For an interstellar object, this is quite unusual, Statistically, a random visitor from deep space could come from any direction, at any angle. But 3I Atlas seems to move along a well-worn road, though of course this is just geometric coincidence. Nevertheless, this makes the object observable from both Earth hemispheres, expanding possibilities for coordinated campaigns. The comet nucleus size remains subject to debate. Estimates range from 600 meters to 5.6 kilometers in length, almost a tenfold difference. Such uncertainty is related to a fundamental problem of observational astronomy. We don't see the nucleus directly. We see light reflected from the nucleus and scattered by the coma, a cloud of gas and dust that surrounds the nucleus and can be hundreds of times larger than the solid body itself. Separating one light source from another is extremely difficult. The James Webb Space Telescope, working in the infrared range, attempted to solve this problem by analyzing the nucleus's thermal radiation. But even its capabilities are limited by distance and coma brightness. As for shape, observations indicate an elongated structure, not as extreme as Oumuamua, but definitely stretched out. This could be the result of a collision in a distant star system, when a larger body was destroyed and its fragments were ejected into interstellar space. Or it's the original shape of a planetesimal, a planetary building block that never became part of a larger world. In our solar system, asteroids and comet nuclei often have irregular, angular shapes, traces of the system's turbulent youth, when objects collided, shattered, stuck together. 3I Atlas may carry memory of similar processes in the system where it was born, possibly billions of years ago, when our sun hadn't yet ignited. Chemical analysis of the coma brought surprising results. The James Webb Space Telescope, pointed at the object in August and September 2025, detected spectral lines of numerous molecules. Water, the basis of cometary material, frozen billions of years ago. Carbon dioxide in high concentration, explaining bright activity even at great distance from the sun. Carbon dioxide sublimates at lower temperatures than water ice. Carbon monoxide, carbonyl sulfide, cyanide. All these molecules are typical for comets, but their ratios can differ depending on formation conditions. Most unexpected was the detection of atomic nickel in the coma. Metals in comets aren't rare. They're part of dust mixed in ice. But nickel in gas phase requires high temperatures for evaporation. This means processes inside the nucleus are heating material to hundreds of degrees. Perhaps this is related to exothermic chemical reactions, when complex organic molecules break down under solar radiation, releasing heat. Or these are traces of ancient radioactive decay of isotopes that were once part of the protoplanetary disk of that distant star where the comet was born. The green coma of 3I Atlas became its calling card. This emerald shade arises from diatomic carbon, a molecule consisting of two carbon atoms bonded together. When complex organic molecules in cometary ice, methane, ethane, longer hydrocarbon chains, break down under the sun's ultraviolet radiation, one breakdown product is diatomic carbon. This molecule fluoresces in the green spectrum range when illuminated by sunlight. Green comets have been observed before. For example, Comet Lovejoy in 2014 showed similar color. But for an interstellar object, this is the first case of such bright green glow, indicating rich carbon compound content. However, 3I Atlas presented scientists with another surprise. In mid-October 2025, observers detected the appearance of an antitail. Usually a comet has two tails, dust and ion. The dust tail consists of small particles ejected from the nucleus and follows the comet's orbit, slightly deflecting under sunlight pressure. The ion tail is formed by charged gas particles blown by solar wind strictly in the direction away from the sun. Both tails always point away from the sun, which is why when a comet moves away from the star, it flies tail first. But an antitail is an optical illusion arising at certain observation geometry, when the comet's dust tail, lying in the orbital plane, is seen almost edge-on. Then the impression is created that the tail points toward the sun, not away from it. The appearance of an antitail at 3I Atlas means the comet passed the point where its orbital plane intersects the line of sight from Earth. This is a geometric event that allows refinement of orbital parameters and understanding of dust distribution in the tail. But the very fact of such a pronounced antitail speaks to a significant quantity of large dust particles that aren't blown by solar wind as easily as fine dust and gas. These particles, sized from fractions of a millimeter to several millimeters, slowly lag behind the nucleus, forming a flat dust disk along the orbit. When we look at this disk almost edge-on, it appears as a narrow beam pointing in an unexpected direction. Another anomaly was discovered when analyzing data from the TESS Space Telescope, Transiting Exoplanet Survey Satellite, a NASA satellite designed to search for exoplanets. In the period from May to June 2025, TESS conducted a series of observations of 3I Atlas, capturing more than 9,000 images. A research team led by Tony Farnham, Max Hood, Michael Kelly, and Jessica Sunshine analyzed this data, searching for signs of cometary activity. Results turned out unexpected. The comet demonstrated a brightness profile almost identical to inactive bodies, asteroids without a coma. This puzzled astronomers. Other observations conducted by ground-based telescopes and the Hubble Space Telescope clearly showed the presence of coma and tail, but TESS data didn't detect a significant cloud around the nucleus. The explanation may be that 3I Atlas's activity is extremely weak compared to ordinary comets. Dust ejection velocity, by estimates, is only about 10 meters per second, several times less than typical comets, where dust flies out at speeds of hundreds of meters per second. At such low velocity, the coma remains compact, tightly pressed to the nucleus, and it's difficult to distinguish from the nucleus itself at low image resolution. There are details about 3I Atlas that make even experienced astrophysicists fall silent. One of them is the object's age. Trajectory calculations conducted using data from the Gaia space mission, a European satellite creating a three-dimensional map of the Milky Way, allowed astronomers to trace the comet's path back in time. When astronomers rewound the orbit backward, unwinding millions of years, they discovered something astonishing. The object didn't come from the nearest neighborhoods, not from young stellar clusters. Its trajectory leads to an area known as the thick disk of the galaxy, a zone populated by old stars. The thick disk is a structural element of our galaxy, located between the thin disk, where the sun and most visible stars are located, and the central bulge. Thick disk stars formed earlier, in the turbulent youth of the Milky Way, when the galaxy was still actively absorbing smaller galaxies and experiencing waves of intense star formation. The age of thick disk stars is estimated at 8 to 10 billion years. If 3I Atlas really comes from there, this means the comet could have formed 7 to 8 billion years ago, almost twice as old as our sun, which is only 4.6 billion years old. Imagine the scale of this journey. When 3I Atlas was forming in the protoplanetary disk of its home star, our solar system didn't exist yet. The Milky Way looked different. Fewer spiral arms, more chaotic stellar motion, regions of active star formation where there's now emptiness. The comet could have witnessed the birth and death of numerous stars, flying past them at distances of light years. Each of these stars left its mark: cosmic rays, matter ejections during flares, gravitational disturbances, And all this time, 3I Atlas preserved material from that ancient era, frozen in its icy nucleus. This makes the comet an invaluable scientific find. Astronomers study the early universe by looking at distant galaxies. Their light travels for billions of years, showing us the past. But that's an image from afar, without details. And here, a physical sample of matter from an era when the galaxy was half its current age, chemical composition, isotope ratios, ice crystal structure. All these are windows to times when conditions were forming in the universe for the emergence of systems like ours. Perhaps in that distant system where 3I Atlas was born, life was also emerging, or already existed, or had long vanished. We'll never know, but the very thought is mesmerizing. However, there's another mystery that haunts researchers. 3I Atlas's velocity relative to the Sun is abnormally high, 58 kilometers per second. For comparison, Oumuamua moved at 26 kilometers per second, Comet Borisov, 32, almost twice as fast as the first interstellar visitor. Where does such energy come from? What gave the comet such a powerful impulse? Astrophysicists are considering several scenarios, and none of them looks definitive. First possibility: gravitational maneuver in the home system. If 3I Atlas formed in a system with a massive planet, a gas giant like our Jupiter but larger, a close pass by this planet could have ejected the comet at tremendous velocity. Such maneuvers are used by humanity's spacecraft. Flying past a planet, a probe steals part of its orbital energy and accelerates. But to reach 58 kilometers per second requires a very massive planet in a very fortunate orbit, or several sequential gravitational maneuvers. The comet pinballed between several giants, gaining speed with each pass until it flew out of the system forever. Second version: supernova explosion. If 3I Atlas's home star was massive and ended its life in a catastrophic explosion, the shockwave could have ejected planetesimals from the system at enormous velocities. A supernova releases in a few seconds as much energy as a normal star radiates over millions of years. Stellar material flies apart at velocities of thousands of kilometers per second. Objects at the system's edges, caught by this wave's impact, could have been ejected into interstellar space. But for a comet 7 to 8 billion years old, this means its star was quite massive. Such stars live no more than a few million years. So the comet formed, was ejected, and has since drifted in interstellar void for almost 8 billion years. Third scenario: encounter with a black hole or neutron star. If 3I Atlas on its path passed near a compact massive object, the remnant of an exploded star, gravitational interaction could sharply change trajectory and velocity. Stellar mass black holes and neutron stars create extreme gravitational fields in immediate proximity. An object flying past experiences the effect of a gravitational sling, accelerating to speeds unattainable with ordinary planetary maneuvers. But the probability of such an encounter is extremely small. Interstellar space is vast, and black holes don't shine. They can only be found by indirect signs. Fourth hypothesis: the most exotic: galactic collision. The Milky Way has absorbed several smaller galaxies over its history. When two galaxies merge, their stars and gas clouds pass through each other. Distances between stars are so great that direct collisions are extremely rare. But the gravitational field changes radically. Stars and planetary systems experience powerful tidal forces. Their orbits distort. Objects from system outskirts can be ejected into space between galaxies at velocities exceeding typical interstellar ones. If 3I Atlas witnessed such an event billions of years ago, its current velocity could be the result of that cataclysm. But there's also a fifth version: spoken about in hushed tones. Uneven gas outgassing from the comet's surface can create reactive thrust, slightly changing trajectory and velocity. This effect has been observed in many comets, including Oumuamua. It's precisely what sparked debates about the first interstellar visitor's nature. If 3I Atlas's nucleus rotates in a certain way and active areas are positioned asymmetrically, gas ejection can work like a natural rocket engine. Over millions of years, such thrust is capable of changing velocity by kilometers per second. But here, a question arises. Where does the energy for this thrust come from? Ordinary comets are only active near stars, when sunlight heats the surface. In interstellar void, temperature is close to minus 270 degrees Celsius. Nothing can sublimate in such cold. Unless there's an internal heat source, radioactive decay of long-lived isotopes, aluminum-26, iron-60, could maintain temperature inside the nucleus above the freezing point of some substances. Carbon dioxide freezes at minus 78 degrees, carbon monoxide at minus 200. If there are pockets of these gases inside the comet, heated by radioactive element decay, slow leakage through cracks in the crust could create weak but constant thrust over millions of years. This is a purely natural process, but its consequences look almost like engine operation. October 22, 2025 added another element to this cosmic drama. A powerful explosion occurred on the Sun, a coronal mass ejection, when billions of tons of magnetized plasma are thrown into space at velocities of hundreds of kilometers per second. And according to astronomers' calculations, this plasma cloud is moving directly toward 3I Atlas. The collision should occur in the coming days, right when the comet passes perihelion and is at minimum distance from the Sun. What will happen in such a collision? A coronal mass ejection is a stream of charged particles carrying a powerful magnetic field. When it strikes 3I Atlas's coma, the magnetic field will interact with ionized gas surrounding the comet. The comet's ion tail may suddenly change shape, brightness, direction. Luminosity bursts are possible, gas fluorescence under the impact of high-energy particle flow. Photographers and amateur astronomers worldwide are preparing their instruments, hoping to capture this moment. A comet colliding with solar plasma is a rare spectacle, and when the comet is interstellar, this event becomes absolutely unique. The change in 3I Atlas's tail direction, recorded in October 2025, itself sparked scientific interest. The Nordic Optical Telescope captured how the anti-tail, that same wrong tail pointing toward the Sun, gradually disappears, and in its place, a normal dust tail forms, directed away from the star. This is explained by changing activity as it approaches perihelion. At the initial stage, when the comet was far from the Sun, carbon dioxide sublimation dominated. It evaporates at lower temperatures. Carbon dioxide ejection was weak, slow. Particles moved leisurely and formed that very anti-tail, an optical illusion of geometry. But as it approaches the Sun, the nucleus surface temperature rises. Water ice begins to sublimate intensely, and there's usually much more water in comets than carbon dioxide. Water vapor flow strengthens, dust ejection accelerates, and a classic comet tail forms, long, curved under sunlight pressure and solar wind. This process is absolutely natural for comets, but observing it in an interstellar object is the rarest chance to see how matter from another star system reacts to our Sun. However, 3I Atlas's behavior remains mysteriously detailed. Astrophysicist Avi Loeb from Harvard University, the same scientist who suggested artificial origin for Oumuamua, rated 3I Atlas at 4 out of 10 on his own Loeb scale. This scale, developed by him to assess the probability that an interstellar object represents alien technology, considers anomalous characteristics, unusual trajectory, atypical acceleration, strange shape, reflectivity, anomalies. 4 points means presence of enough anomalies to keep the question open, but insufficient for serious claims about artificiality. Loeb is known for his willingness to consider radical hypotheses. In an interview, he called 3I Atlas a Trojan horse, possibly just a metaphor for an object that hides more than it shows. But in the context of conspiracy theories and speculation bubbling on social media, this comparison takes on an ominous tone. What if the comet isn't just a comet? What if something else hides beneath the shell of ice and dust? Official science categorically rejects such suggestions. All observations point to natural origin. Composition is typical for comets. Behavior is explained by sublimation physics. Shape corresponds to expectations for a planetesimal fragment. And yet, IAWN activation sparked a wave of discussions. On social media, they quote the phrase, "When all telescopes from Mauna Kea to Chile synchronize on one object, this is no longer a drill." The observational campaign, scheduled from November 27, 2025 to January 27, 2026, will include all available resources, professional and amateur telescopes, spacecraft, tracking systems. Such a level of coordination is truly unprecedented for an object that, according to official data, poses no threat. NASA's explanation is prosaic. This is training of the International Threat Response System, using a rare interstellar object as a training target. Data collected during the campaign will allow improvement of methods for determining precise location of fast-moving objects, test coordination between observatories in different countries, work out protocols for real-time information exchange. All this is reasonable, logical, consistent with planetary defense objectives, but in an era of information noise, any official explanation is perceived by part of the public with suspicion. October 29, 2025, Perihelion Day, will be the critical point. After this moment, 3I Atlas will begin moving away from the Sun, heading toward the system's outer regions. December 19, 2025, date of maximum approach to Earth, 1.8 astronomical units, about 270 million kilometers. Safe distance, twice as far as from Earth to the Sun. No collision threat, but it's during this period that the comet will be most accessible for Earth observations. Close enough to collect detailed data, but already past the Sun in the night sky. In late November, the comet will appear in the constellation Virgo. Brightness will be at the limit of visibility for amateur telescopes, around 11th to 12th magnitude. Invisible to the naked eye, but a modest telescope with 15 to 20 centimeter diameter will show a faint spot with hints of coma and tail. Thousands of amateur astronomers worldwide will point their instruments at this point in the sky, hoping to capture the visitor from the interstellar abyss. Each photograph, each measurement, will add a fragment to the overall picture, a mosaic of understanding what 3I Atlas is and where it came from. The chemical composition of 3I Atlas is a text written in the language of molecules. Every substance detected in the coma, every element ratio, is a word in the story about the system where the comet was born. And astronomers are learning to read this text, letter by letter, spectral line by spectral line. August 2025 became a turning point in this decryption process. When the comet was at a distance from 3.2 to 2.9 astronomical units from the Sun, telescopes at the MDM Observatory at Kitt Peak in Arizona first detected optical gas emission in the coma. This was a moment of awakening. Before this, the comet was almost silent, a cold chunk of ice and rock rushing through the void. But as it approached the Sun, surface temperature rose enough to trigger sublimation. the first gas molecules broke free from the icy prison where they'd spent billions of years. An international team of astronomers conducted a 10-day observation campaign from August 8th to 17th, obtaining spectra and photometric data daily. Each night, telescopes captured the comet's light, broke it down into component colors, and in this rainbow spectrum searched for characteristic dark absorption lines and bright emission lines, signatures of specific chemical elements and molecules. Cyanogen was detected first, the CN molecule, consisting of a carbon atom and nitrogen atom. Cyanogen emission in the comet's spectrum appears as a bright line in the blue-green region. Cyanogen is toxic to Earth life, but its presence in comets is absolutely natural. It forms when more complex organic molecules break down under the sun's ultraviolet radiation. But the intensity of this line was weaker than expected. And what's stranger, signals from more complex carbon molecules that usually accompany cyanogen in comet spectra were absent. Astronomers called this phenomenon carbon chain depletion. In typical solar system comets, molecules like C2, diatomic carbon, which creates the green glow of the coma, C3, triatomic carbon, and longer chains are present. These molecules form from organic substances frozen in cometary ice during system formation. But in 3I Atlas, these complex carbon structures are either present in much smaller quantities or absent altogether. This could point to two scenarios. Either in the star system where the comet was born, organic formation processes differed from ours, or over billions of years of interstellar journey, these molecules degraded under cosmic rays and interstellar radiation. Cosmic rays are high-energy particles, mainly protons and helium nuclei, that permeate the galaxy. They're born in supernovae, in pulsars, in active galactic nuclei, and travel nearly at light speed, carrying energy sufficient to break molecular bonds. An object that spent billions of years in interstellar space undergoes continuous bombardment by these particles. The surface ice layer gradually degrades. Complex organic molecules break down into simpler fragments. The process is slow, but relentless. Over 1 billion years, cosmic rays can alter the chemistry of the upper centimeters of cometary material beyond recognition. Perhaps what we see in 3I Atlas's spectrum isn't the comet's original composition, but the result of billions of years of radiation exposure. But there's a more intriguing possibility. Chemical composition reflects conditions in the star system where the comet formed. Planet formation processes depend on many factors: stellar mass, its metallicity, distance from the galaxy's center, presence of neighboring stars. A thick disk galaxy star born 7 to 8 billion years ago had different chemical composition than our young sun aged 4.6 billion years. Early stellar generations were poorer in heavy elements, carbon, nitrogen, oxygen, because these elements are born inside stars and spread through the galaxy only after supernova explosions. Each stellar generation enriches the interstellar medium with heavy elements, and the next generation forms from richer material. If 3I Atlas is truly that ancient, its composition may reflect the chemistry of the young galaxy, times when there was less carbon and nitrogen, and complex organic molecule formation processes went differently. This is a hypothesis requiring confirmation, but the very fact of possibly studying matter from such a distant era captures the imagination. Usually we look at the ancient universe through telescopes, observing light that traveled for billions of years. But light is just photons, information is limited. And here, a physical object, matter that can be analyzed spectroscopically, isotopic composition determined, compared with laboratory samples. This is archaeology on a cosmic level. The James Webb Telescope added its findings to this mosaic. Working in the infrared range, where most molecules have characteristic spectral signatures, Webb detected the presence of water vapor, carbon dioxide, carbon monoxide, carbonyl sulfide, and, unexpectedly, atomic nickel. Water was expected. It's the main component of any comet. Carbon dioxide explains early activity. It sublimates at temperatures below -78 degrees Celsius, long before water ice begins to evaporate. Carbon monoxide and carbonyl sulfide are typical breakdown products of more complex carbon compounds. But nickel in gas phase is a mystery. Metals don't evaporate at temperatures characteristic of a comet's surface even near the sun. Temperature on the illuminated side of a comet nucleus, at 1.5 astronomical units from the star, can reach 50 to 100 degrees Celsius, sufficient for intense ice sublimation, but completely insufficient for nickel evaporation, whose boiling point is about 2,900 degrees. So where does nickel in the coma come from? Possible explanation: exothermic chemical reactions inside the nucleus. When sunlight penetrates the upper layers of porous ice, it destroys complex organic molecules. Some of these reactions release heat. In pores and cracks, temperature can locally rise to hundreds of degrees. In these hot pockets, metallic dust mixed in ice begins to heat up. Nickel, present as fine particles measuring microns, can evaporate from their surface. Gas flow bursting from the comet's depths captures these nickel atoms and carries them into the coma. There, in the comet's rarefied atmosphere, nickel atoms fluoresce under sunlight, creating characteristic spectral lines that the telescope detects. A similar process has been observed in some solar system comets, but for an interstellar object, this is the first case of such detailed metallic composition analysis. The nickel ratio to other elements can tell about the composition of that protoplanetary nebula where the comet formed billions of years ago. The green glow of the coma, recorded in September 2025, became 3I Atlas's calling card. This emerald shade is created by fluorescence of diatomic carbon, the C2 molecule. When solar ultraviolet hits this molecule, it transitions to an excited state, then returns to ground state, emitting a green light photon with wavelength around 510 nanometers. This is the exact shade characteristic of Earth's aurora, where a similar process occurs with oxygen atoms in the upper atmosphere. Green comets aren't rare. For example, Comet Lovejoy in 2014 and Comet Lemon in early 2025 showed similar glow. But for an interstellar object, this is the first observed case. An interesting feature of diatomic carbon: it doesn't survive to the comet's tail. The C2 molecule is extremely unstable under sunlight. Its lifetime in the coma is about a day. Then it breaks down into individual carbon atoms. That's precisely why green glow is concentrated around the comet's nucleus in the immediate coma and doesn't extend to the tail. The tail, consisting of fine dust and simple molecules like water and carbon dioxide, has a pale yellow or white color, reflected sunlight without significant fluorescence. This color boundary, green coma and white tail, creates a characteristic visual image instantly memorable to observers. But what does C2's presence say about the comet's origin? Diatomic carbon forms during photolysis, light destruction, of larger organic molecules. In solar system comets, these are usually hydrocarbons, methane, ethane, acetylene, and more complex structures. When solar ultraviolet breaks bonds in these molecules, C2 appears among breakdown products. The fact that we see green glow at 3I Atlas means carbon compounds capable of producing C2 upon breakdown are present in the comet's nucleus. This indirectly indicates organics presence, albeit in a form altered by cosmic rays. The comet carries carbon, the basis of life as we know it. carbon from another star system, but still chemically identical to ours. This fact has deep consequences for astrobiology. If organic molecules form in planetary systems throughout the galaxy, if processes are similar regardless of where and when a star was born, this strengthens the panspermia hypothesis, the idea that life or its building blocks can spread between star systems. Comets ejected from their home systems wander the galaxy, carrying organic substances. From time to time, they enter other systems, as 3I Atlas entered ours. If such a comet collides with a planet that has suitable conditions, water, atmosphere, moderate temperature, organics from the comet can become a seed for life's emergence, or at least enrich the planet's chemical composition, adding molecular diversity necessary for complex biochemical processes. Of course, this is speculation. We don't know if there was life in the system from which 3I Atlas came. We don't even know if that star still exists. If it was massive and exploded as a supernova, only a compact remnant remains, a neutron star or black hole. The planetary system destroyed, and the comet flies on, carrying the last traces of that world. This is an almost poetic vision. The comet as a tombstone of a long-vanished star system, a silent monument to a civilization that maybe never even arose. October 8, 2025, the comet was at a distance of 237 million kilometers from the Sun and 370 million kilometers from Earth. Brightness slowly increased as it approached perihelion. Photometric observations showed gradual luminosity increase, a sign of intensifying activity. More ice sublimates, more dust ejects, the coma expands. Calculations showed, on perihelion day, October 29th, brightness will reach maximum, around 10th to 11th magnitude, not visible to the naked eye, but accessible to binoculars and small telescopes. Thousands of amateur astronomers prepared for this moment, checking equipment, choosing observation sites away from city light pollution. But precisely in the days around perihelion, the comet will be in line with the Sun. Solar conjunction will make Earth observations impossible. The object will hide in the blinding light of the day star for several weeks. This is a critical period when activity is maximum, but we can't see it directly. But spacecraft will come to the rescue. The SOHO Solar Observatory, operating at the Lagrange point between Earth and Sun, is equipped with a coronagraph, an instrument that blocks direct sunlight and allows observation of the area around the Sun. Over its more than 25 years of operation, SOHO has detected thousands of comets approaching close to the Sun. 3I Atlas may enter the coronagraph's field of view in late October, and then we'll see how the interstellar comet passes perihelion, the brightest and most active moment of its visit. Late November 2025, the comet will appear in the morning sky, low above the eastern horizon before dawn, in the constellation Virgo. Brightness by then will drop to 12th to 13th magnitude, still accessible to amateur telescopes with 15 to 20 centimeter diameter, but requiring dark sky and good observation conditions. December will bring further dimming. The comet will move into the constellation Leo. Brightness will fall to 14th magnitude and below. By year's end, 3I Atlas will be accessible only to large professional telescopes, and then dissolve into the blackness of interstellar space, carrying its secrets away. December 19, 2025, day of maximum approach to Earth. Distance, 1.8 astronomical units, about 270 million kilometers. Safe distance, no threat, but symbolically significant. This is the last moment when the interstellar visitor will be relatively close. After this, it will begin moving away ever faster, gaining speed as it exits the solar system's gravitational well. In a year, it will be beyond Saturn's orbit. In 10 years, beyond the Kuiper Belt. In a century, in interstellar void. where no one will ever see it again. October 23rd, 2025 triggered a chain reaction not only in the astronomical community, but in public space as well. News about IAWN activation spread at a speed exceeding the comet's own velocity. Social media exploded with discussions. Forums dedicated to space and conspiracy theories recorded record traffic. Hashtags related to 3I Atlas hit top trends in almost all English-speaking countries and many other regions of the world. And this isn't surprising. The combination of words interstellar object and planetary defense creates a cocktail of curiosity, anxiety, and thrilling possibilities for imagination. The information age created a paradox. Access to scientific data has never been easier, but distrust of official sources has never been so widespread. When NASA publishes a statement about 3I Atlas's safe trajectory, part of the audience perceives this as confirmation, meaning there's something to hide. When a space agency activates a coordinated observation campaign, this is interpreted not as scientific interest, but as a sign of concern. Conspiratorial thinking logic works in reverse. The more denials, the stronger the conviction in the opposite. Statements by Avi Loeb played a special role in this information storm. An astrophysicist from Harvard University whose academic reputation is impeccable, but whose public statements often balance on the edge of provocation. Loeb became famous for his willingness to consider hypotheses that most colleagues reject as too radical. It was he who suggested Oumuamua might be an artificial object, a solar sail of an alien civilization. The scientific community met this idea skeptically, pointing to numerous natural explanations for the first interstellar visitor's anomalous acceleration. But for the public, Loeb became a symbol of a scientist who dares to think beyond the accepted. His rating of 3I Atlas at 4 out of 10 on his own Loeb scale became a meme almost instantly. This scale, developed by the scientist for quantitative assessment of the probability of artificial origin of interstellar objects, considers various anomalies: unusual shape, atypical acceleration, strange spectral characteristics, deviations from expected behavior. 4 points means presence of enough anomalies to keep the question open, but insufficient for serious claims. For Loeb, this is methodological caution. For the internet, confirmation of something unusual. In one interview, Loeb used the Trojan horse metaphor when discussing 3I Atlas. Perhaps it was just literary imagery, a way of saying the object might hide more than it shows at first glance. But in the context of conspiracy theories, this phrase took on an ominous tone. The Trojan horse is a symbol of hidden threat that penetrates protected space under the guise of a harmless gift. Applied to a comet, this sounds like a warning. Something else could be hiding under the shell of ice and dust. Technology, a probe, an observation device. The scientific community categorically rejects such speculation, pointing out that all data corresponds to a natural cometary object. But public skepticism is amplified by the scale of coordinated observations. From November 27, 2025 to January 27, 2026, an unprecedented campaign is planned, including professional and amateur telescopes worldwide, spacecraft, tracking systems. A phrase circulates on social media. When all telescopes from Mauna Kea to Chile synchronize on one object, this is no longer a drill. The argument is understandable. Why such resources for an object that, according to official data, will pass at a safe distance and poses no threat? NASA's official explanation is logical and consistent. This is training of the International Threat Response System, a rare opportunity to work out protocols on a real, albeit safe object. Data collected during the campaign will allow improvement of methods for determining precise location of fast-moving objects, test coordination between observatories in different countries, work out real-time information exchange. This makes sense from the standpoint of preparing for a real future threat. Interstellar objects are rare. Missing the opportunity to use one as a training target would be wasteful of scientific resources, but in an age of distrust, any rational explanation can be reinterpreted as a cover-up. This isn't specific to astronomy. It's a characteristic feature of the 21st century information landscape. When official institutions lose their monopoly on information distribution, space emerges for alternative narratives. Some are harmless, fantasies and speculation that satisfy human need for wonder and mystery. Others are more problematic. They undermine trust in science as such, creating an atmosphere of constant doubt. History knows many examples of panic related to celestial phenomena. October 30th, 1938, Orson Welles' radio play, War of the Worlds, caused panic among listeners who took the artistic dramatization for a real report about a Martian invasion. Although the panic's scale was probably exaggerated by media of the time, the incident itself showed how easily reality and fiction blend when it comes to space and potential threats. In the 21st century, this boundary became even more blurred. Social media creates echo chambers where alternative interpretations of events amplify and become more convincing for those already predisposed to believe them. 1997, comet Hale-Bopp approached the Sun, becoming one of the year's brightest celestial objects. Theories appeared that an alien spacecraft was following the comet. A group of people in California, members of the Heaven's Gate cult, took this literally. They believed the ship had come to collect their souls and committed mass suicide to free themselves from physical bodies and join the aliens. 39 people died. This tragedy is an extreme example of how pseudoscientific speculation can have real and horrifying consequences. The scientific community recognizes this responsibility. When astronomers talk about 3I Atlas, they try to balance honesty about uncertainties with clarity about what's known for certain. The object demonstrates anomalies. This is fact. Its velocity is unusually high, age impressive, chemical composition shows deviations from typical solar system comets. But anomalies don't equal alien technology. In science, an anomaly is simply an observation requiring additional study. Most anomalies in science history were explained by natural processes we didn't yet fully understand. Take pulsars, neutron stars emitting regular radio wave pulses. When Jocelyn Bell and Anthony Hewish discovered the first pulsar in 1967, the signal was so regular that astronomers jokingly called it LGM-1, Little Green Men. It was a joke, but it reflected a moment of amazement. Nature created something so precise, it resembled an artificial signal. Further research showed this was a natural process, a rotating neutron star with a powerful magnetic field. But the lesson remained. The universe is capable of what looks incredible without resorting to intelligent design. Same with 3I Atlas. Green coma, anti-tail, high velocity, ancient age. All this fits within natural processes, albeit rare, albeit not fully understood. The comet came from the galaxy's thick disk, a region of old stars where chemistry and dynamics differ from our region of the Milky Way. It spent billions of years in interstellar void, subjected to cosmic ray exposure, which altered its surface layer. It was ejected from its home system at enormous velocity, possibly by gravitational maneuver, possibly by supernova explosion, possibly by encounter with a compact object. All these are permissible scenarios within known physics. October 22nd added another element of drama, a coronal mass ejection on the Sun, a cloud of magnetized plasma moving toward 3I Atlas. The collision should occur in the days around perihelion, when the comet is at minimum distance from the Sun. This is a natural phenomenon, unrelated to the comet itself. The Sun regularly ejects plasma, especially during high-activity periods. But the temporal coincidence creates a sense of drama. The interstellar visitor meets our star's wrath. Interaction of the plasma cloud's magnetic field with the coma's ionized gas may change tail shape and brightness, create fluorescence bursts, possibly even cause fragmentation of weakly bound nucleus parts. Astronomers and photographers are preparing to capture this moment, but observations are complicated by solar conjunction. The comet is hidden in the day star's light during the most critical days. Only space coronagraphs, such as aboard the SOHO Observatory, will be able to see what's happening. The rest of the world will have to wait until late November, when 3I Atlas appears in the morning sky in the constellation Virgo, having already passed perihelion and begun the long journey away from the solar system. There's a beauty in this waiting. Humanity has looked at comets as omens for millennia, sometimes favorable, more often ominous. Halley's Comet appeared in historical chronicles hundreds of times, and almost every time its presence was linked to earthly events, wars, deaths of kings, epidemics. Of course, these connections were illusory, a product of human tendency to seek patterns and meaning in random coincidences. But the emotional resonance remained. Comets inspire awe. They come from darkness, cross the sky in radiance, return to the unknown. They remind us of the scales of space and our smallness in this abyss. 3I Atlas amplifies this effect many times over. This isn't just a comet. It's a visitor from another world, in the most literal sense. Every photon of light reflected from its surface and captured by our telescopes carried information about something born in a different star system. Perhaps that system had planets. Perhaps one of them had conditions for life. Perhaps life emerged there, evolved, created civilization, or died before that, or never appeared. We'll never know, but the very possibility of asking these questions while looking at a specific physical object is mesmerizing. Science lives in the space between known and unknown. The known is the foundation on which theories are built. Laws of physics, chemical processes, mathematical models. The unknown is the horizon toward which research strives. Every new object, whether an interstellar comet or distant galaxy, expands the map of the known and simultaneously opens new areas of the unknown. 3I Atlas will provide answers to some questions about chemical composition of matter in the galaxy's thick disk, about processes of ejecting objects from planetary systems, about interstellar medium's impact on cometary material, and simultaneously spawn new questions. That's exactly how science works. October 29, 2025 will remain in calendars as the perihelion day of 3I Atlas, the day when the interstellar wanderer came closest to our sun, felt its warmth after billions of years of cold, began losing material, molecule by molecule, dust, particle by dust particle, leaving a glowing trail behind, and then continued its journey, accelerating, leaving the gravitational well, returning to interstellar void. In a year, it will be beyond Saturn. In 10 years, past the Kuiper Belt. In a century, in the cold darkness between stars, where no one will ever see it again. But data collected during these few months of observations will be analyzed for years, decades, possibly centuries, each generation of astronomers finding something new in them that previous generations couldn't see. The uniqueness of the moment humanity is experiencing in the fall of 2025 lies not only in the very fact of an interstellar visitor's arrival. For the first time in history, we have a fleet of spacecraft capable of observing such an object from different points in the solar system, at different angles, in different ranges of the electromagnetic spectrum. When Oumuamua rushed through the system in 2017, it was discovered too late. The object was already departing, and almost no time remained for detailed study. Comet Borisov in 2019 was luckier to meet us more prepared, but even then, most observations were conducted from Earth. 3I Atlas caught us at a moment of unprecedented space activity. October 3rd, 2025, the comet passes by Mars at a distance of 28 million kilometers. For cosmic scales, this is practically a touch. The object's brightness from the red planet's perspective reaches 11th magnitude at the very limit of orbital camera visibility. The European Space Agency decides to direct its Martian spacecraft at this target, ExoMars. Trace Gas Orbiter, a satellite designed to study Mars's atmosphere and search for signs of methane, turns its instruments toward the passing comet. Spectrometers tuned to detect trace amounts of gases in the Martian atmosphere prove ideal for analyzing the cometary coma. Mars Express, a veteran of Martian exploration operating in orbit since 2003, joins the observation campaign. Its high-resolution cameras capture the structure of coma and tail from an angle unavailable to Earth telescopes. From Mars's perspective, the comet is visible at an angle allowing distinction of the dust cloud's three-dimensional structure. What looks like a flat projection from Earth reveals itself in volume from Mars. Data is transmitted to Earth in portions as the spacecraft pass over zones of ground antenna visibility. Each communication session brings new images, new spectra, new confirmations or refutations of hypotheses. But Martian observations are just the beginning. In October 2025, several recently launched spacecraft are moving through the inner solar system, heading toward their targets. Europa Clipper, NASA's flagship mission to Jupiter's moon Europa, launched in late 2024 and is now on a trajectory leading to gravitational maneuvers at Earth and Mars. The mission schedule aligned its trajectory with 3I Atlas's trajectory at a critical moment. In late October, the spacecraft will be in a position allowing it to fly through the outer regions of the comet's tail. This isn't a planned encounter. When Europa Clipper was designed and launched, no one knew about 3I Atlas's existence. But space mechanics worked out favorably. The mission's science team quickly assessed possibilities and made a decision. Activate the spacecraft's instruments to collect data during passage through the tail. Europa Clipper is equipped with a mass spectrometer, an instrument capable of determining the chemical composition of individual molecules. In normal mode, it should analyze particles from Europa's hypothesized subsurface geysers. But now it can capture molecules from an interstellar comet's tail, a direct sample of matter from another star system. A comet's tail isn't a dense formation. At a distance of several million kilometers from the nucleus, particle concentration is extremely low, a few molecules per cubic meter. For comparison, air at sea level contains about 10 to the 19th power molecules per cubic meter. The comet's tail is 1,000,000 billion times more rarefied, but Europa Clipper's mass spectrometer is so sensitive it can register individual molecules. Each captured particle will be analyzed, elemental composition determined, isotope ratios measured, molecular structure identified. This data will allow comparison of 3I Atlas material with solar system comet material at the atomic nucleus level, the most fundamental level. Isotopes are variants of one element with different numbers of neutrons in the nucleus. For example, carbon exists in two stable forms, carbon-12 and carbon-13. The ratio of these isotopes in matter depends on the conditions in which it formed: temperature, pressure, presence of certain chemical reactions. Solar system comets have a characteristic isotope ratio reflecting conditions in the protoplanetary disk 4.5 billion years ago. If 3I Atlas shows a different ratio, this will be direct proof that formation conditions in that distant system differed from ours, or that the matter's age is truly so great that isotope composition changed due to radioactive decay of long-lived isotopes. Another spacecraft ends up in a favorable position for observations. Hera, a European Space Agency mission to the binary asteroid Didymos launched very recently, also adjusts its trajectory to collect comet data. Hera is equipped with cameras and LiDAR, a laser rangefinder capable of measuring distances with centimeter accuracy. Although the spacecraft won't approach 3I Atlas's nucleus closely, its instruments can capture the structure of the tail's outer parts, measure dust particle velocity, determine their size distribution. Each such data fragment adds to the overall picture, the mosaic of understanding how an interstellar comet behaves under our sun's influence. Coordinating these observations requires the most precise planning. Spacecraft can't simply turn and point instruments at a random target. Each maneuver requires calculations, checks, commands from Earth. Communication with spacecraft travels at light speed, but even light needs time. A signal from Mars to Earth takes 3 to 22 minutes depending on the planet's mutual position. Europa Clipper is still relatively close, but in years, when the spacecraft reaches Jupiter, signal delay will exceed 40 minutes one way. Now, in October 2025, mission operator teams work around the clock, calculating observation windows, sending commands, receiving data, analyzing results. On Earth, telescopes prepare for the critical moment. October 29th, perihelion day, the comet will be hidden in the sun's light for most ground-based instruments. But the SOHO Space Observatory, operating at Lagrange point L1 between Earth and Sun, is equipped with the LASCO coronagraph, an instrument that blocks direct sunlight and allows observation of the area around the solar disk. Over more than 28 years of operation, SOHO has detected about 4,000 comets, most of which were small fragments falling onto the sun and burning in its corona. But 3I Atlas will pass at a safe distance of 1.36 astronomical units. It won't fall onto the star, but will swing around it and return to space. If the trajectory and coma brightness prove sufficient, LASCO will be able to capture the historical moment, the interstellar visitor at the brightest point of its visit, shrouded in intensely sublimating gas and dust, possibly with several tails, dust and ion, stretched over millions of kilometers. Photographs of such an event will enter textbooks, become iconic images of the era. Just as the blue marble shot, a photograph of Earth from Apollo 17, became a symbol of the 70s space era, an image of an interstellar comet near the sun may become a symbol of our time, a moment when humanity learned not just to look at space, but to study it in its fullness. October 22nd added a dramatic element to this cosmic drama. A powerful coronal mass ejection occurred on the sun, a sudden release of billions of tons of magnetized plasma into space. Such ejections happen regularly, especially during high solar activity periods. The 11-year solar activity cycle in 2025 is close to maximum. The plasma cloud moves at velocities from 300 to 2,000 kilometers per second. And according to astrophysicists' calculations, this particular ejection's trajectory leads directly toward 3I Atlas. A plasma cloud collision with a comet is rare but not unique. Usually comets collide with solar wind, a constant stream of charged particles the sun radiates in all directions. Solar wind forms the comet's ion tail, blowing charged gas molecules strictly away from the sun. But a coronal mass ejection isn't constant wind, it's a hurricane. Particle density in the cloud is hundreds of times higher than in normal solar wind. The magnetic field frozen in plasma carries energy capable of tearing weakly bound structures. When the cloud reaches 3I Atlas, and this should occur in the days around perihelion, the comet's ion tail may suddenly change shape, brightness, direction. The plasma's magnetic field interacts with the coma's ionized gas, creating turbulence. Gas particles accelerate to high velocities, fluoresce more intensely than usual. Disconnection events are possible, situations when part of the ion tail completely separates from the comet under magnetic forces and is carried away by solar wind. Such events have been observed in several solar system comets and look dramatic. The tail suddenly disappears, then begins forming anew from fresh gas ejected by the nucleus. For 3I Atlas, this will be a trial by fire, literally, considering the plasma temperature of hundreds of thousands of degrees. But physical impact on the comet's nucleus is minimal. Plasma is extremely rarefied. Even in a dense coronal ejection, the number of particles per cubic centimeter numbers in the millions, which is still trillions of times less than Earth's atmospheric density at the surface. The cloud will pass through the coma like a ghost through a wall, leaving no physical damage, but changing everything visible. Astronomers and photographers prepare to capture this moment, understanding the window of opportunity is narrow. The comet is almost in line with the sun. Observations are difficult. But if someone manages to catch the interaction in a photograph, this will be an image that enters history. Late October to early November becomes a period of waiting. The comet is hidden behind sunlight. Ground-based telescopes are helpless. They can't be pointed so close to the sun without risk of damaging optics. Only SOHO and possibly the James Webb Space Telescope operating at Lagrange point L2 beyond Earth's orbit can attempt to collect data. But Webb isn't designed for observing objects so close to the sun. Its enormous sun shield protects sensitive infrared optics, but simultaneously limits field of view. The mission team assesses possibilities, calculates risks, decides whether to attempt observation or decline. During this time, astronomers worldwide analyze data collected before perihelion. Coma spectra obtained in August, September. October contain hundreds of spectral lines, signatures of various molecules and atoms. Each line requires identification, calibration, interpretation. The ratio of different molecules changes as it approaches the sun, reflecting changes in nucleus surface temperature. At 3 astronomical units distance, carbon dioxide dominates. It sublimates even at low temperatures. At 2 units, water ice begins to evaporate. At 1.5 units, activity reaches maximum. Gas and dust ejection is so intense, it creates pressure capable of tearing weakly bound nucleus parts. Comet fragmentation is a common phenomenon. Comet nuclei aren't monolithic. They're rather loose conglomerates of ice, dust, and rocks, weakly bound by gravity and frozen gases. When sublimation intensity exceeds structural strength, the nucleus splits. Sometimes small fragments separate. They quickly lose material and disappear. Sometimes a comet breaks into several large parts, each continuing to actively evaporate. The history of comet observations is full of such breakup examples. Comet Schwarzmann-Wachmann 3 broke into dozens of fragments during perihelion passage in 2006. Comet Ison, which in 2013 approached too close to the sun, completely disintegrated, leaving only a dust trail. Will 3I Atlas survive perihelion passage? A distance of 1.36 astronomical units is a relatively safe distance. Comets regularly pass much closer and survive. But 3I Atlas spent billions of years in the cold of interstellar space. Its ice structure may differ from comets in our system. Prolonged cosmic ray exposure could have altered the crystalline lattice, created internal stresses. When such ice suddenly heats up, it can behave unpredictably. Explosive sublimation, internal cracks, fragment separation. All these are possible scenarios. We'll only learn about this when the comet emerges from behind the sun in late November and becomes visible to ground-based telescopes. November 27, 2025, the first opportunity to see the comet after perihelion. By this point, it will be in the constellation Virgo, low above the eastern horizon before dawn. Brightness is forecast at 11th to 12th magnitude, accessible to amateur telescopes with 15 to 20 centimeter diameter under dark sky. On this day, the official international observation campaign coordinated by IAWN begins. Hundreds of observatories worldwide will direct their instruments at one point in the sky. Professional astronomers and amateurs will unite efforts, creating a continuous data stream. Late November 2025 will bring a moment astronomers await with impatience and anxiety. November 27th, the day when 3I Atlas will appear for the first time after passing perihelion in the pre-dawn sky, far enough from the sun that ground-based telescopes can point their optics at it without risk. First images will show: did the comet survive the trial by fire? Did the nucleus remain intact or break into fragments, each now moving along a slightly different trajectory? Did activity intensify after perihelion? Or conversely, did the comet lose so much material that it's now fading faster than forecasts? The history of comet observations knows many surprises. Some comets pass perihelion and become brighter than expected. Fresh ice layers, exposed after solar heat stripped off the outer crust, begin sublimating intensely. Others disappoint. The nucleus turns out smaller than thought, or covered with a thick layer of dark dust that insulates the ice and suppresses activity. Still others simply disappear, break into small fragments that quickly lose all volatile material and turn into dim rocks, invisible even to large telescopes. Each comet is unique, and predicting behavior with absolute precision is impossible. For 3I Atlas, uncertainty doubles due to its interstellar origin. Solar system comets are studied well enough. Thousands of observations over centuries created a statistical base allowing reasonable predictions. But interstellar comets? We have only two previous examples. Oumuamua showed no cometary activity at all. Its nature remains a mystery. Comet Borisov behaved like a typical comet in our system, but still demonstrated some peculiarities in chemical composition and activity. 3II Atlas is the third example, and it's already shown it doesn't fit into simple categories. The constellation Virgo will become home to the comet in late November. This is an extensive sky area located on the ecliptic, the imaginary line along which the sun moves among stars from an Earth observer's perspective. Virgo is one of the zodiacal constellations, and its position means the comet will be visible low above the horizon before dawn. For observers in the northern hemisphere, conditions aren't ideal. The object rises only 10 to 15 degrees above the eastern horizon before dawn. Twilight makes the sky too bright. In the southern hemisphere, conditions are better. There, Virgo rises higher, gives more time for observations in dark sky. Brightness at 11th to 12th magnitude means the comet will be at the limit of binocular capabilities. In ideal conditions, absolutely dark sky, far from cities, without the moon, an experienced observer with 50 millimeter diameter binoculars can distinguish a faint spot in the indicated area. But this will require patience, dark adapted vision, precise knowledge of where to look. A 15 to 20 centimeter diameter telescope will show the comet confidently, a small, fuzzy cloud, possibly with a faint hint of tail, if activity remains at sufficient level. Professional observatories have prepared their observation programs. November 27th, official start of the international campaign that will last until January 27th, 2026. 2 months of continuous tracking of the departing comet. Every night, when weather permits, dozens of telescopes worldwide will record the object's position, measure its brightness, obtain spectra for chemical composition analysis. Coordination is carried out through the International Asteroid Warning Network, the very system whose activation on October 23rd caused so many questions and speculation. The campaign's goal is multi-layered. On the surface, working out international coordination in tracking a fast-moving object. This really is training, but training on a real target, where mistakes and successes will be visible immediately. Deeper, collecting maximum volume of scientific data about the rarest phenomenon. Interstellar objects don't come often. Statistical models predict that several such objects pass through the inner solar system each year, but most are too dim for detection by modern telescopes. We only see the brightest, largest. Missing the opportunity for detailed study of 3I Atlas would be a scientific crime. Even deeper, testing hypotheses about the object's nature. Despite official statements about natural origin, the scientific method requires checking all reasonable alternatives. Measuring precise trajectory with high resolution will show whether there's anomalous acceleration, a sign of non-gravitational forces such as reactive thrust from gas ejection. Photometry, measuring brightness changes, can reveal periodicity, indicating rotation of an asymmetric body. Spectroscopy will show whether the coma's chemical composition changes as it moves away from the sun, when different types of ice successively stop sublimating with falling surface temperature. December 19th, 2025, the campaign's culmination. On this day, 3I Atlas will reach the point of maximum approach to Earth, 1.8 astronomical units, about 270 million kilometers. This is almost twice as far as the distance from Earth to the Sun. No threat, no danger. But for astronomers, this is the optimal moment. The comet is close enough that telescopes can collect details that at greater distances are lost in noise. The coma's angular size will reach maximum. Spectral lines will be brighter, easier to analyze. Every night around December 19th will be used at full capacity. By this time, the comet will have moved into the constellation Leo. Brightness will probably drop to 13th to 14th magnitude, already beyond the capabilities of most amateur telescopes, but still accessible to instruments with 30 to 40 centimeter diameter and larger. Professional observatories with 1 meter and 2 meter mirrors will see the object confidently. The Hubble Space Telescope and James Webb Telescope will continue their observations, collecting highest quality data, spectra with resolution unattainable for ground-based instruments, images of coma and tail with detail allowing distinction of gas jets bursting from active areas on the nucleus surface. Late December will bring gradual dimming. The comet moves away from the sun, its surface temperature drops, sublimation slows. Gas and dust ejection decreases, the coma shrinks, the tail fades. By the end of 2025, brightness will fall to 15th magnitude, accessible only to large professional telescopes. January 2026, the last month when the object can be observed regularly. Brightness will continue falling. 16th magnitude, 17th. The comet fades not only physically, losing material as gas and dust, but also visually, dissolving into the blackness of space. January 27th, 2026, official completion of the International Observation Campaign. But this doesn't mean the end of observations. Individual observatories equipped with the largest instruments will continue tracking for more weeks, possibly months. Each additional measurement refines the orbit, gives better understanding of non-gravitational forces, improves models of cometary activity. But for most astronomers, 3I Atlas will by this time become inaccessible, too dim, too distant. The comet will pass beyond Mars's orbit, heading toward the system's outer regions. Data collected over these months will be analyzed for years. Hundreds of thousands of images, spectra, photometric measurements. Each dataset needs to be calibrated, processed, compared with theoretical models. Astronomers will write papers, publish results, argue about interpretations. 3I Atlas's chemical composition will be compared with solar system comet composition. Element by element, isotope by isotope, the ratio of carbon-12 to carbon-13 will show at what temperatures cometary material formed. The ratio of deuterium, heavy hydrogen, to ordinary hydrogen will tell about water exchange processes between gas and ice in that distant system's protoplanetary disk. The object's trajectory will be recalculated with maximum precision. Each observation of sky position is a point on the curve describing the comet's path through the system. The more points, the more accurate the curve. Mathematical methods will allow separation of gravitational attraction from the Sun and planets from non-gravitational acceleration caused by gas ejection. The magnitude and direction of this acceleration will tell about how active areas are distributed on the nucleus surface, how fast the comet rotates, how asymmetric the shape is. All this, details that add up to a portrait of an object that came from another world. Photometric data, brightness change curves, may reveal periodicity. If the comet's nucleus is asymmetric, and elongated shape suggests exactly this, brightness will change with rotation period. When the long axis points toward us, reflected area is maximum, brightness higher. When the object turns sideways, area decreases, brightness drops. By measuring these oscillations, rotation period can be determined. For comets, typical periods range from several hours to several days. Fast rotation indicates a dense, well-bound nucleus. Slow rotation may mean loose structure or recent breakup into fragments when angular momentum redistributed. But beyond dry numbers and scientific papers, 3I Atlas will leave a mark on culture. The first interstellar comet to become an object of mass attention. Social media, news feeds, conspiracy theories, artistic interpretations. Photographers and videographers worldwide will capture the green coma against stars. Thousands of astronomy enthusiasts who never looked through a telescope before will buy or rent an instrument to see the visitor from the depths of space with their own eyes. Teachers in schools will talk about interstellar objects, showing children that the universe is bigger and more complex than it seems. Science fiction writers will write stories about comets carrying messages or artifacts of vanished civilizations. These cultural reflections of a scientific event are no less important than the data itself. Science doesn't exist in a vacuum. It's part of human culture, a way of understanding the world and our place in it. When the general public becomes interested in a comet, asks questions, argues about interpretations, this is a sign of a living, healthy connection between science and society. Even conspiracy theories, for all their problems, reflect a deep human need for wonder, for meaning, for the sense that the universe is full of mysteries not yet revealed. Scientists' task isn't to mock these needs, but to channel them productively, to show that real science is no less and often more captivating than any fiction. 3I Atlas will depart, in a year, beyond Saturn's orbit. In 10 years, in the Oort cloud, a cold region at the system's edges where trillions of comet nuclei reside, awaiting the moment when gravitational perturbation will send them toward the sun. But 3I Atlas won't remain there. Its velocity is too great, the sun's gravity too weak to capture the interstellar wanderer. In 100 years it will be an interstellar void, moving toward a new random destination. Perhaps in 1,000,000 years it will enter another star system. Perhaps there will be astronomers who discover it and ask the same questions we do. Or perhaps it will drift in void for billions more years until it encounters something, a star, planet, black hole, or dissolves under cosmic ray action and collisions with interstellar gas, turning into a dust cloud that someday will become part of a new star, new planets, new comets. The cycle continues. The matter of the universe is immortal. Only forms change. There's a particular irony in the fact that an object that spent billions of years in absolute solitude of interstellar void, in the final months of its visit to our sun, finds itself under the close attention of billions of beings on a small blue planet. Every night, thousands of telescopes, from amateur tubes a few centimeters in diameter to giant professional instruments with mirrors measured in meters, are pointed at one spot in the sky, tracing the path of a dim speck of light among the stars. Spacecraft adjust trajectories, sacrificing precious fuel to conduct a few hours of observations. Supercomputers process petabytes of data, building models that try to explain every detail of the comet's behavior. The James Webb Telescope science team decided to conduct a second series of 3I Atlas observations in December 2025. The first series in August yielded a rich harvest of data, spectra showing the presence of water, carbon dioxide, carbon monoxide, organic molecules, and unexpected atomic nickel. But these were pre-perihelion observations when the comet was just beginning to awaken under solar heat. December observations will show a different picture. The object, after maximum heating, possibly changed, possibly having lost a significant portion of volatile substances, possibly exposing deeper layers that were hidden under the surface crust for billions of years. Webb's infrared cameras are particularly sensitive to thermal radiation. Even when the comet moves away from the sun and its temperature drops, residual heat will radiate in the infrared range for weeks and months. By analyzing this radiation, astronomers can determine the thermal conductivity of the nucleus material, how quickly heat penetrates inside and dissipates. High thermal conductivity indicates dense structure with good contact between particles. Low thermal conductivity is characteristic of loose, porous bodies where there's much empty space between grains. This information is critical for understanding how the nucleus formed, through slow accretion of small particles or collision and sticking of large fragments. Another spacecraft got a chance to contribute to studying the interstellar visitor. JUICE, Jupiter Icy Moons Explorer, a European mission to Jupiter's moons, launched in 2023 and now on the long journey to the gas giant, will be in a favorable position for observations in early November. From November 2nd to 25th, JUICE will direct 5 of its scientific instruments at 3I Atlas: cameras, infrared imager, ultraviolet spectrometer. This will be observation just days after perihelion, when the comet is in its most active state. From JUICE's perspective, located far from the ecliptic plane, observation geometry will be completely different than from Earth or Martian orbital spacecraft. But there's a problem. JUICE's position relative to Earth in November 2025 is such that data transmission speed is extremely low, only a few kilobits per second. At such speeds, transmitting gigabytes of scientific data will take months. Olivier Witas, European Space Agency project scientist, estimated JUICE observation data will arrive on Earth only in February 2026. We'll have to wait. But the wait is worth it. These will be observations of an interstellar comet from a unique angle, with instruments designed to study icy worlds. An opportunity that won't repeat. December 17, 2025. A date some researchers pointed to as a key moment in studying 3I Atlas. Close to the 19th, when maximum approach to Earth is expected. The 2-day difference is insignificant from a scientific standpoint. The trajectory is smooth, changes gradual, but symbolically, these dates in mid-December will become the culmination of months of preparation and observations. Astronomers will get the last opportunity to collect high-quality data before the comet begins rapidly fading, moving beyond Mars's orbit, then Jupiter's, then dissolving into the cold darkness of the system's outer regions. What will remain after 3I Atlas's departure? First of all, data. Terabytes of images, spectra, photometric measurements. Each observation contains information that needs to be extracted, analyzed, interpreted. This process will take years. Young graduate students who in 2025 are just beginning their scientific careers will defend dissertations based on 3I Atlas data in the late 20s and early 30s. Professors will publish review articles summarizing decades of research in the 40s. Astronomy textbooks written in the 50s will use 3I Atlas as a classic example of an interstellar comet, alongside Oumuamua and Borisov, 3 pioneers who paved the way for understanding that interstellar space isn't empty, that the galaxy is full of wanderers, and from time to time, they visit us. The technological legacy is also significant. The International Observation Campaign, coordinated by IAWN, became the largest in scale and longest in duration in planetary defense history. Protocols worked out on 3I Atlas, from detection and initial classification to coordination of hundreds of instruments worldwide, will form the basis of future operations. When, and this will inevitably happen, the system detects an object posing a real collision threat to Earth, experience-accumulated tracking an interstellar comet will prove invaluable. Every problem found, delays in data exchange between observatories, standardization format issues, difficulties coordinating observations across time zones, was documented and solved. The next campaign will be more efficient. Cultural impact is harder to measure, but no less real. Photographs of 3I Atlas's green coma against stars went viral on social media. Artists created visualizations, imagining what the comet would look like from close range. Irregularly shaped nucleus covered with dark crust of organic tars, cracks from which gas jets burst, backlit by sunlight. Composers wrote music inspired by the theme of interstellar travel. Slow, melancholic melodies conveying the infinity of time and space the object crossed. Science fiction writers used 3I Atlas as a starting point for stories about messages, artifacts, time capsules drifting between stars. In schools, teachers told children that the universe isn't confined within our solar system's boundaries. That matter travels between stars. That one day, perhaps, humanity will also send its probes to other systems. And from those worlds' perspective, they'll become interstellar objects, possibly evoking the same curiosity and speculation that 3I Atlas evoked in us. This thought of reciprocity, that we look at space and space looks at us through interstellar wanderers, is a powerful idea expanding perception horizons. Scientific discussions about 3I Atlas's origin will continue long after its departure. Chemical composition analysis, comparison of isotope ratios with solar system comets, trajectory modeling backward in time. All this requires thoroughness and time. The hypothesis of 7 to 8 billion years age, based on presumed origin from the galaxy's thick disk, needs confirmation through studying isotopes of long-lived radioactive elements. The ratio, for example, of thorium-232 to uranium-238 can indicate material age. These isotopes decay slowly, with half-lives in billions of years, and their ratio changes over time predictably. Measuring these ratios is extremely difficult for a distant object, but not impossible. High-resolution spectroscopy, especially in the ultraviolet range, can provide needed data. Another question astronomers will investigate: did 3I Atlas's trajectory change during passage through the system? Non-gravitational acceleration from gas ejection isn't just a scientific detail, it's a key to understanding the comet's internal structure. The magnitude and direction of this acceleration are determined by active area distribution on the surface, nucleus rotation rate, object mass. By comparing the comet's sky position predicted by a purely gravitational model with observed position, non-gravitational forces can be calculated. If these forces prove larger than expected for a natural comet, this will spawn new questions. If smaller, will confirm natural origin. Memory of 3I Atlas in public consciousness will gradually fade as the comet itself fades, moving away from the sun. In a year, news cycles will switch to other events. In 5 years, most people not connected with astronomy will forget about the green comet that caused so much talk in fall 2025. But in the astronomical community, memory will persist. Every scientific paper using 3I Atlas data will cite the first observations made by the Atlas telescope in Chile on July 1st. Every textbook discussing interstellar objects will mention the third visitor, after Oumuamua and Borisov, but before those who will come later, and they will come. Statistical models updated with recent years' discoveries predict each year the probability of detecting new interstellar objects grows, not because there are more of them. Their number in interstellar space remains roughly constant. But our telescopes are getting better. Automatic sky survey systems like ATLAS, Pan-STARRS, the future Vera Rubin Survey Telescope, scan the entire sky every few nights, capturing everything that moves, everything that changes. Machine learning algorithms trained on Oumuamua, Borisov, and 3I Atlas data have learned to recognize characteristic signs of interstellar origin: high velocity, hyperbolic trajectory, unusual spectral characteristics. The next interstellar object may be discovered in a year, or in 5 years, or already discovered but not yet classified. Data awaiting analysis on observatory servers. Each such discovery will supplement the picture. The third example gave more information than the first two, simply because we were better prepared. The fourth will give even more. The 10th will allow building statistical generalizations. The 100th will become routine. And somewhere between the 10th and 100th will cross the understanding threshold, the moment when interstellar objects stop being mysteries and become just another type of celestial body with its own patterns, its own classification, its own predictable properties. But until this threshold is crossed, each interstellar visitor is unique. 3I Atlas will forever remain the third, the first to show a green coma, the first with such high orbital eccentricity, the first whose age is estimated in billions of years, the first for which the planetary defense system was activated. These firsts can't be taken away. Even when hundreds of others are discovered, 3I Atlas will retain its place in astronomy history as the comet that taught us to look deeper, think broader, prepare better. October 23, 2025, the day of IAWN activation, will enter the chronology of planetary defense system development as the day when protocols created after the Chelyabinsk meteorite were applied in full scale to an object that came from outside our system. This wasn't a day when humanity repelled a threat. There was no threat. It was a day when humanity showed readiness to act in coordination when a real threat comes. A rehearsal day before the real performance, which we hope will never happen. But if it happens, we'll be ready. Thanks to 3I Atlas. Thanks to thousands of astronomers, engineers, spacecraft operators who spent months tracking a green point of light crossing the sky, we now know the system works. International coordination is possible. Data is collected, analyzed, distributed. Protocols function, and somewhere in interstellar void, at distances light travels for years, other objects drift. Fragments of planetary systems ejected by gravitational maneuvers or stellar explosions. Icy comet nuclei that will never see a nearby star. Perhaps among them are artifacts, probes, capsules, messages from civilizations that also ask the question, are we alone? And sent their answers in bottles across the ocean of space and time. We haven't found such messages yet, but we keep searching. With each new telescope, with each new algorithm, with each new discovery like 3I Atlas, we expand the boundaries of the known and approach answers to humanity's most ancient questions about our place in space. There's a particular melancholy in observing departing objects. Doesn't matter if it's a ship disappearing beyond the ocean's horizon, or a plane dissolving into clouds, or a comet fading each night, receding into the depths of space. This melancholy isn't about loss, rather about the completion of a moment that was unique and won't repeat. 3I Atlas passed through our system in several months, but its presence left a trace that will be discernible for decades. Not a physical trace, though dust particles from its tail will drift in interplanetary space for centuries, but a trace in knowledge, in data, in how we understand the universe and our place in it. February 2026 will bring long-awaited data from the JUICE spacecraft. 2 months of waiting while information transmitted at a speed of several kilobits per second, slower than the first internet modems in the 90s. But patience will be rewarded. Observations conducted from November 2nd to 25th captured the comet in its most active state, just days after perihelion. 5 scientific instruments worked synchronously. Cameras recorded the visual structure of coma and tail. The infrared imager measured thermal radiation. The ultraviolet spectrometer analyzed gas composition. From JUICE's perspective, located far from the ecliptic plane, the geometry was unique, an angle that will never repeat for this object. The data will show details invisible from Earth. 3-dimensional coma structure, dust distribution by particle size, direction and velocity of gas jets bursting from active areas on the nucleus surface. Each of these details is a puzzle piece that astronomers will assemble for years. The comet's nucleus, according to refined data from the Vera Rubin Observatory, has a diameter of 11.2 kilometers, plus or minus 0.7 kilometers. This is larger than initial estimates. The object turned out impressive, one of the largest interstellar visitors we've ever seen. Such size explains the brightness that initially seemed anomalous and sparked speculation. 3I Atlas's brightness at first detection truly surprised. Professor Abraham Loeb from Harvard pointed out that for a natural object, such brightness at so great a distance from the sun requires enormous size. The statistical probability of detecting such a large interstellar comet is indeed small, but not zero. We live in a galaxy with 300 billion stars, each of which could potentially have ejected planetesimals into interstellar space over billions of years of existence. Rare events are inevitable in a sufficiently large sample. And here, one such rare specimen ended up on our doorstep, within reach of our telescopes. The dust coma surrounding the nucleus proved key to understanding brightness. Dust reflectivity is high. Fine particles sized in microns effectively scatter sunlight in all directions. When the coma expands to tens of thousands of kilometers in diameter, total reflecting area becomes enormous. despite extremely low matter density. Each cubic meter of coma contains only a few thousand dust grains, but the coma's volume numbers in trillions of cubic meters. Cumulatively, this gives brightness comparable to a small planet, though the entire coma's mass is only fractions of a percent of the solid nucleus mass. Detection of hydroxyl gas by the Swift Orbital Observatory became important confirmation of the object's cometary nature. Hydroxyl, the OH molecule, consisting of an oxygen atom and hydrogen atom, is a photolysis product of water. When the sun's ultraviolet radiation destroys an H2O molecule, it breaks down into OH and atomic hydrogen. Hydroxyl fluoresces in the ultraviolet range, creating a characteristic spectral line that ground-based telescopes can't see. Earth's atmosphere absorbs this light, but the Swift Space Telescope, working high above the atmosphere, catches this faint glow, invisible from below. Hydroxyl's presence is water's chemical fingerprint, direct proof that 3I Atlas's nucleus contains water ice sublimating under sunlight. Water on an interstellar comet isn't just a chemical detail. It's confirmation that planetary system formation processes throughout the galaxy are similar. Water is one of the simplest and most common compounds in the universe. Oxygen is born in massive star interiors and spread by supernova explosions. Hydrogen is a Big Bang legacy, the first element to appear in the universe. When a gas cloud cools, oxygen and hydrogen combine, forming water. In the cold of protoplanetary disks, water freezes, becomes ice, coats dust grains, glues them into larger aggregates that ultimately grow into planetesimals, asteroids, comets, planets. This process is universal, and 3I Atlas is living proof of this universality. The comet disappeared from view in late October, hiding in the sun's light. Solar conjunction made observations impossible. The object too close to the day star, risk to telescopes too great. Astronomers waited, reviewing calculations, updating models, preparing instruments for the moment when 3I Atlas would reappear in the sky. Late November brought this return. The comet appeared in the pre-dawn sky, low above the eastern horizon, dimmer than before perihelion. Part of volatile substances was lost, activity decreased, but still accessible for observations. The international campaign resumed at full strength. A peculiarity of 3I Atlas's trajectory was its close coincidence with the ecliptic plane, deviation of only 5 degrees. This means the comet moves almost in the same plane where solar system planets rotate. For a random interstellar object that could come from any direction, this is statistically improbable, but not impossible. Of many objects entering the system at different angles, some will inevitably end up close to the ecliptic plane simply by the law of large numbers. But this coincidence, combined with retrograde motion, the object moves in the opposite direction to planetary rotation, creates a visually impressive picture. The trajectory passes near Mars in October 2025 and near Jupiter in March 2026. For conspiratorially minded people, this looks like a series of calculated gravitational maneuvers, as if someone specifically plotted a route past major planets. But a gravitational maneuver requires precise calculation and active trajectory correction. A natural object entering the system on a hyperbolic trajectory moves along a path determined only by the sun's and planets' gravity. If this path accidentally passes near several planets, this is precisely accident, albeit impressive. Astronomers calculated the trajectory backward and forward for millions of years, and no signs of controlled movement or anomalous accelerations that can't be explained by cometary activity were found. Enhanced water evaporation, about 40 kilograms per second, at a distance of nearly 3 astronomical units from the sun, initially seemed anomalous. Ordinary solar system comets at such distance are either inactive or demonstrate weak activity, mainly through carbon dioxide sublimation. But 3I Atlas proved unusually active even far from the Sun. Possible explanation: a depleted surface layer lacking the heavy organic crust that usually insulates internal ice of comets in our system. Billions of years in interstellar space under cosmic ray action could have eroded the surface, stripped the protective layer, leaving nearly pure ice close to the surface. When sunlight reaches this ice, sublimation begins intensely, even at great distances. Observations also revealed deep negative light polarization, minus 2.7% at 7-degree angle. Polarization of light reflected from particles depends on their size, shape, composition. Negative polarization indicates presence of very fine particles, submicron size, that scatter light in a special way. This says that dust in 3I Atlas's coma differs from typical cometary dust in our system, where particles several microns in size dominate. Perhaps this is the result of a different dust formation process in that distant system, or a consequence of a long interstellar journey, when collisions with interstellar gas gradually fragmented particles into ever smaller pieces. Over the past 4.7 million years, no celestial body exerted serious gravitational influence on 3I Atlas. This conclusion is based on backward trajectory calculation considering positions of all known stars in this galaxy region. The comet drifted in interstellar void, far from stars, experiencing no significant perturbations. The nearest star on its path was HD 187760, located 84 light-years from Earth. 3I Atlas flew past it about 72 years ago. The star's gravity practically didn't affect the trajectory. Distance was too great, velocity too high. The comet simply passed by like a ship in the night, not noticing the star, and the star not noticing the comet. Over millions of years of travel, the object could have encountered 93 stars. Each encounter, weak gravitational attraction, slightly curving the trajectory. The sum of these microscopic changes over millions of years determined the path that brought the comet to our sun. Random wandering on grand scales. Each star adds a small vector to the trajectory, and the resulting path seems chaotic, but is actually strictly determined by gravity laws. If it were possible to know with absolute precision the position and velocity of each star millions of years ago, 3I Atlas's trajectory would be predictable to the centimeter. But we know star positions only approximately, and uncertainty accumulates with each million years until it becomes comparable to the galaxy's own dimensions. January 27th, 2026 will officially complete the International Observation Campaign. But observations will continue for more weeks, possibly months. The largest telescopes will track the fading point until it completely disappears into the noise of background stars. Each additional measurement is valuable because it increases the observation arc, the time interval during which we track the object. The longer the arc, the more precise the orbit, the better we understand where the comet came from and where it's heading. By campaign's end, 3I Atlas's observation arc will exceed 7 months, from July 1st, 2025 to February 2026. This will be one of the longest arcs for an interstellar object, exceeding in duration Oumuamua observations and comparable to Comet Borisov observations. Data is already beginning to bear fruit that will develop for years. Young researchers are choosing dissertation topics related to chemical composition analysis, trajectory modeling, studying dust dynamics in the coma. Professors are planning review articles that will summarize everything known about the third interstellar visitor. Planetary scientists are comparing 3I Atlas with comets in our system, seeking similarities and differences that will tell about planetary system formation processes in different corners of the galaxy and in different epochs of its history. Astrobiologists are studying organic molecules and spectra, assessing how rich interstellar matter is in life's building blocks. And somewhere in interstellar void, other objects drift, thousands, millions, possibly billions of planetary system fragments ejected on infinite journeys. Some move fast, like 3I Atlas, crossing the galaxy in hundreds of millions of years. Others slowly, drifting in local currents between stars. From time to time, one of them enters a foreign system, maybe ours, maybe a system around a distant star we'll never know about, and in that moment, it stops being an invisible wanderer and becomes an object of study, curiosity, possibly fear, possibly admiration. 3I Atlas left, but its visit left something important, not answers. Answers are never enough in science. Each answer spawns new questions. But it left a path, a method, experience. The next interstellar visitor will be met by better prepared instruments, more experienced astronomers, more efficient coordination protocols. Each visit teaches us something new about the galaxy, about processes that connect star systems with invisible threads of matter exchange. And one day, perhaps in centuries, humanity itself will send its probes to other stars, and from those worlds' perspective, they'll become interstellar objects, messengers from a distant blue planet where intelligent beings looked at the sky, asked questions about their place in space, and found answers in the light of comets that came from the darkness between the stars.